Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it: planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, Director of Planetary Science at NASA, and this is Gravity Assist. I'm here at JPL, the fabulous place in Pasadena, California, that make a lot of dreams happen, and they do some remarkable missions. And one of the missions going to Mars that we want to talk about is the InSight mission. And I'm here with Bruce Banerdt, the principal investigator for NASA's InSight mission. Welcome, Bruce. You know, one of the neat little things that you have, and that is a name, Bruce Banerdt, and isn't that the Hulk?
It is. It is the Hulk, and I just have to tell, don't make me mad. I mean, you can ask me about it, but just be careful here.
All right, I understand that completely, and I don't plan on doing that. What does InSight stand for? It's an acronym, just like everything else NASA does, seems to be.
So InSight stands for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. And if you put the capitals and the lower cases together right, you get InSight.
All right, that sounds cool. Well, a couple parts to that we want to really tease out. Seismic investigation. You know, what is that all about? What does that mean?
Well, a seismic investigation is really the heart of this mission. Seismology is the method that we've used to gain almost everything we know, all the basic information about the interior of the Earth. And we also used it back during the Apollo era to understand and to measure sort of the properties of the inside of the moon. And so we want to apply the same techniques, which use the waves that are generated by Marsquakes, by meteorite impacts, to probe deep into the interior of Mars, all the way down to its core.
You know, that's a fascinating concept. You would have thought that we've had seismometers on Mars before. You know, why is it taking us so long?
Well, we did send seismometers once before, back during Viking, but it was kind of an afterthought on that mission, which was mostly focused on looking for life on Mars. And so it was like it was attached to the top of the deck, and they didn't have the resources to have some method of putting it onto the surface. And, you know, it was just sort of a shot at the buzzer, seeing if they could get something. But since the seismometer's on the deck and it's trying to measure very subtle vibrations on the ground, it wasn't very sensitive, and over the course of the mission, mostly what it measured was just the wind blowing the spacecraft around. So we really haven't had what I would consider a top-notch seismic investigation of the planet.
Okay, I understand that part of it. In fact, what it did tell us is what not to do, right? And what we had to do. And so that means the seismic system that's going to be on InSight is really well prepared, in that you're going to have to move it to the ground, and you're going to have to protect it from the wind. And so how are you going to do that?
Well, we've put a lot of thought into it, as you can imagine. I mean, on the Earth, you put a seismometer kind of in the basement of a building, in a vault, and you keep the temperature really constant, and you don't have any air moving through, and so forth. On Mars, we're putting it out on the surface in a really harsh environment. And so what we've done is we put a robotic arm on the spacecraft, first of all, that'll pick it up off the deck, move it out in front of the spacecraft, about 2 meters away from the spacecraft, and put it down in a place that we find that has no rocks, no holes, so that it's nice and stable. Once it's out there, it already has built into it 2 different layers of protection. It's inside a spheroidal enclosure that has a very hard vacuum, so it's like being inside a thermos bottle. And then we have around that some thermal blanketing that protects it some more from the temperature. But once it's on the surface, we go back with our robotic arm and pick up what we call our wind and thermal shield, which is like a big upside down walk with a curtain next to on the sides. We put it over the seismometer. It's actually got some chain mail around the bottom that'll drape over rocks and kind of seal the bottom against the wind blowing in underneath. And so at that point, the seismometer is pretty well protected from the elements, although it's still going to experience that huge temperature variation that Mars sees from day to night.
You know, these instruments, these seismic instruments that you're going to put on Mars, I think they're the most sensitive seismic instruments ever made.
Well, that's not quite true. I mean,
Oh,
there's some that on the Earth that are a little bit more sensitive, especially at long periods. You know, with when waves are have periods that are hundreds of seconds long. You know, long rolling waves. That's really difficult to do, and it takes some fairly heavy electronics and heavier mechanical systems. But in terms of the sensitivity of a small seismometer, a portable seismometer, these really are what well, I was going to say world class, but obviously they're solar system class.
how many quakes do you expect to get?
Well, we've done a lot of analysis on that, and the short answer is we don't really know. But of course, being scientists, we got to try to figure it out. And so we've looked at Mars. Mars is crisscrossed by faults, and we can kind of date, find out how old a lot of those faults are. We can measure about how much displacement has been on those faults and figure out how many quakes that took. And so we can chart out sort of the amount of seismic activity over the life of the planet. And some of these faults go back billions of years, and we extrapolate that rate to the present. And of course, it's dying off with time as Mars cools down. And when we extrapolate it to the present, you come up with a level of activity, a frequency of occurrence that gives us an idea that we'll probably see somewhere around 50 quakes during the course of our mission. Of course, that could be off by quite a bit, but we have a reasonable confidence that we should see something, between maybe 20 and 100 quakes over the 2-year life of this mission.
We're sitting out here in California, and it sometimes quakes. And so, what are the kind of things that you can do that would compare the data that we get here on Earth with those on Mars?
Well, I mean, when you feel a quake, I mean, that's a lot of motion, right? I mean, sometimes it's enough to shake your house down. What we're actually looking for on Mars are not the ones that are going to, knock the spacecraft over. We're looking at quakes that happened on the other side of the planet, because what we really want to see are waves that radiate out from these quakes and pass through the deep interior of the planet and then come back up and are then sensed by our seismometers. So it's like, in California, we have seismometers that routinely pick up quakes that happen in Japan, that happen in India and the Middle East. And we use those quakes, use the waves from those quakes to probe the deep interior. So you got waves, they start out at the quake, and then they pass through the rocks of the Earth. And as they pass through those rocks, they change their character depending on the properties of the rocks. You can think of it as kind of picking up information as the waves travel through. And then once we sense them with our seismometer, and you make those wiggly plots you've seen of seismograms, we have techniques to take those wiggles and analyze them, the shape of the wiggles, their frequency, their amplitude, their timing, and sort of pull out that information and start putting together a picture of the inside. I mean, we think of sometimes as quakes as being like little flash bulbs that go off and they illuminate the interior, and our seismometer is the camera that picks up the reflected energy, and over time we can use that to put together kind of a 3D picture of the inside of the planet.
Well, as you say, we are scientists, and so we always have our own models. So we must have some sort of model of the structure of Mars that the seismic information will really straighten us out. What's Mars's structure like?
Well, all the terrestrial planets, all the rocky planets, have a similar structure, and we know that from gravity measurements, from measurements of their dynamics and so forth. And we know that the planets have a very dense metallic core, mostly iron and nickel, surrounded by a mantle of very dense silicate rocks. With a high density because of the pressure that they're under, and then it's surrounded by a crust of the kinds of rocks that you can pick up in your backyard, and those rocks have a lower density, and they in fact probably floated to the surface early in the planet's history. And so we have a more or less 3-layer system, core, mantle, and crust, of differing properties. What's really critical is understanding the details of that structure. What's the size of the core? Is it pure iron? Does it have other elements in it like sulfur or carbon? What's the structure of the mantle? Does it have mostly iron silicates, or is there more magnesium in there? That turns out to be a critical parameter. And then the crust, how thick is the crust? What's the mineralogical composition of the crust, and how much of the radioactive material in the original chondritic dust that made up the planets, how much of that has been moved into the crust through the process of differentiation. That process tends to concentrate the radioactive materials, and that has a big effect on the heat flow, on the thermal state of the interior, and on things like volcanism and tectonism.
Well, here on Earth, we believe we have aspects of a liquid core. Uh, is that true on Mars? And can SEIS be able to tell us if that core is solid or liquid?
Well, we have data from orbital measurements that indicates that the core, at least the outer part of the core, is probably liquid. I mean, we can see by the variation of the planet's rotation under the influence of the sun's tides that is probably liquid. InSight will be able to tell for certain whether it's liquid or solid by looking at the waves that travel through the core. Liquids can support P waves, the compressional waves in earthquake waves, but it can't support S waves, shear waves, because those require a bending stresses, which you can't have in a liquid. So we'll be able to tell for sure whether the outer core is liquid. Whether there's a solid inner core like the Earth, that's a tough thing to figure out. If we stay there long enough and we get enough really good data, we might start to be able to see all the way deep into the center of the core to see whether it's solidified in the center or not.
One of the things that you mentioned that really struck me is, the planet is cooling. All our planets are still in the process of cooling off. It's like, they were baked in an oven, you pull them out and the cake is still cooling off.
Yeah.
So that means we need to measure its heat flow. And you have another fantastic instrument on InSight that does that.
That's right. And the heat flow from a planet is really a measure of, the energy that's driving the geology of the planet. So if you see mountains, if you see giant valleys that are formed by rifts or volcanoes, those are all being driven by the heat flow of the planet, as well as fault activity. The plate tectonics on the Earth is driven by the Earth's heat engine. So the heat is coming up from the deep interior, driving these motions, and then being radiated out to space. So we know that Mars does not have plate tectonics. We can see that because there's no evidence of that kind of faulting on the surface. But we also know that it is radiating heat. It's got a history of volcanism, and it does have many faults on the surface, even though they're not organized as plate boundaries. And that faulting is, we think, mostly driven by the contraction of the planet. As the heat flows out of the planet, it contracts just like anything. As it cools off, contracts. And as it contracts, it crumples a little bit. And that crumpling is manifested in quakes and seismic activity.
So this instrument is called HP3?
Yeah, it's called the HP3, which stands for the Heat Flow and Physical Properties Package. And it's a really kind of an interesting and cool instrument, because it has a little torpedo about a foot and a half long and about an inch in diameter, and it has inside a hammer. It's a kind of a hammer. It has a motor that winds up a mass on a sort of a helical a track and pulls it up against a very stiff spring, and it gets to the top and lets go and goes pow down against the nose of it, and it knocks itself down into the soil just a few millimeters at a time, bang, 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 and it does that about 10,000 times and can burrow down up to 5 meters deep into the below the Martian surface.
Now, of course, that's on the deck originally, and you've got to use the arm and pick it up and situate it.
That's right. That's our third deployment activity with the robotic arm. Yeah, the arm has like 3 main jobs. It has to get the seismometer on there, has to put the cover on the seismometer, and then it goes back and gets the heat flow probe. And because we have to do things really carefully and get it right the first time, it's going to take us a couple of months to go through that whole process.
Well, what's really neat, as you say, this hammer as it operates, is the seismic instrument on during that time period?
It is going to be on during that time period, and this isn't this isn't the main goal of the mission, but it's really cool because those seismic waves from the hammer knocking into the soil, they're going to go bouncing around underneath the surface, and we will probably be able to see what kind of layering there is in the top 20, 30, maybe even 50 feet of the Martian surface. We think there's actually more or less hard lava flows beneath this layer of kind of broken up soil and gravel on Mars, and we should be able to get reflections off that and see whether it's even more solid at depth, and that should be really interesting for people. And it's actually kind of interesting when we think about astronauts going to Mars in the future, because building things on sand is not the smartest way to go about putting up buildings and stuff. So we'd like to understand kind of what the strength is of the Martian regolith, so that when we do send people there, we'll know what kind of geotechnical techniques to use to make structures.
Yeah, absolutely. The kind of measurements that you make just in those two areas could be very important for human exploration of Mars in the future.
Mm-hmm.
But you're not done. You've got other instruments on InSight.
Oh, that's right. I mean, well. First of all, once we burrow down, what that heat flow package does is the actual instrument isn't in the torpedo. The actual instrument is in the cable that connects it back up to the surface. And every couple feet along that cable, we have a little temperature sensor, and those temperature sensors measure not only what the temperature is underneath the surface, but it's measuring how much the temperature is increasing as you go down. And it's only increasing by hundredths of a degree, but we measure it very precisely, and we can extrapolate that increase in temperature down deep into the planet. And that's how we actually understand how much heat is coming out of the planet.
So then in addition to HP3 and the seismic instrument, SEIS, you have wind measurements that you make, cameras.
Yeah, we've got a whole meteorological package. It measures the wind, the speed and the direction of the wind. It also measures pressure variations, so it's a sort of a barometric experiment as well, plus the temperature of the atmosphere. So we have a sort of a complete weather package on there that will be running 24.6 hours a day. And all
which is
through
the length
year.
of the Mars day.
That's right. And we're planning to put up a page on the internet with this sort of weather on Mars, sort of like weather.com except for Mars, and you'll be able to see what the weather was like on Mars yesterday. I don't think we're going to be predicting very much, but we at least being able to tell what the weather's like, that's going to be something cool.
Well, one of the things you told me just a little while ago that I was really excited about is the app on your phone that you guys are thinking of pulling together.
Yeah, we're trying to put together a Marsquake app. The USGS has an app that'll it'll buzz you when there's an earthquake that's happened somewhere on the planet. You can go and check it out. We're going to do the same thing for Mars. We're going to have a Marsquake app. So it's running on your phone and it starts buzzing in your pocket, and you pick it up and it says, "Oh, there was a Marsquake out in Tharsis Plateau yesterday, and check it out." So we hope to be able to get that. It's not going to be in real time because it takes a couple of days to get the data down. But as soon as we get it on the servers, it's going to go out to the public, and that should be a lot of fun.
Well, you mentioned also that the quakes could be from impacts.
Yeah. So when a meteorite hits Mars, it's going to make a pretty big seismic signature. We can have pretty small impacts because the Martian atmosphere is so thin. Even things the size of a golf ball are going to come in and make a crater. And if it's close enough to InSight, we'll be able to pick those up. And the cool thing about that is once we've gotten an impact event on our seismometer, we can go back and talk to the MRO orbiting spacecraft and the high-resolution, high-rise camera and say, "Hey, go check out this area here. We've got an impact that happened, somewhere within, maybe 10 kilometers of this place. Go see if you can see anything new there." And they've already kind of blanketed the area around InSight with before pictures, and they'll go and do the after pictures and see whether they can see a new crater. And if they can do that, that actually helps us a lot too, because then we know exactly where it was, and then we can use all the information from the seismogram to look at the interior and not kind of waste some of it on figuring out where the Marsquake was.
Yeah, no, that sounds spectacular. That's got so many dimensions about it that are really fundamental planetary science, and the ability to get this data and then compare it with Earth, I think is really revolutionary and tells us a lot about how these planets are built. The fact that Mars is smaller than Earth might have been put together a little differently. The core might be a different ratio in terms of its size than the Earth's core. Mm-hmm. And so settling some of these questions can really help us on how our solar system was formed. Well, It's coming up, the launch. Where are you launching from?
We're launching from Vandenberg, California, which is a first for planetary launches. All the other launches to the planets have gone off from Florida. We're in kind of a unique situation in that we have a relatively small spacecraft that was designed for a relatively small rocket, and those small rockets aren't available anymore. They've kind of gone out of production, and so we are on an Atlas V rocket, which has about twice as much capability to go into space as the Delta II that our spacecraft that when it was Phoenix was originally designed for. So instead of having to go to Florida and using the Earth's rotation to help slingshot us into orbit, we don't have to use that. We can blast our way straight out, into a polar orbit. By moving to California, that kind of took some of the pressure off of the traffic jam they tend to have over in Kennedy Space Center. Lots of rockets trying to go off there. We were able to relieve them of some of the pressure. Plus, we get to launch in a way that is going to be visible to maybe 10 million people in Southern California, because this rocket is going to go right by LA, right by San Diego, and if people are willing to get up at 4 o'clock in the morning, they should see a pretty cool light show that day.
Yeah, May the 5th coming up.
That's Cinco de Mayo.
That's right. So May the 5th it launches.
That's right.
Goes straight south, goes under the South Pole, and then takes this mean left turn on its way to Mars.
That's right.
So when does it get there?
It gets there on November 26th, which is Cyber Monday, right after Thanksgiving. And that's true whether we launch right at the beginning of our launch period or later on if there's a weather delay or some kind of an issue with the rocket. Whenever we launch over the 5 weeks that we have available to us, it's going to get to Mars on that same day.
Oh, that's fantastic. Well, I'm going to be celebrating both the launch and the landing.
You better believe I will too.
One of the things that I ask all the guests that come on this podcast is really about their gravity assist. Gravity assist is a planetary term, but in reality, people, places, and things that affect our ability to think about what we're going to do and how we're going to do it, what we're going to do when we grow up, that's a gravity assist. So what was your gravity assist that got you on a direction to become the scientist you are today, Bruce?
My gravity assist was the Mercury program. Okay, when I was 5 years old, Scott Carpenter was blasted into space on top of what looks today like a tiny little rocket. And my mother insists that I only learned to read so that I could read the newspaper articles about the Mercury program. And I was just completely fascinated and completely entranced by the idea of people going into space. And so I just followed the space program, and I wanted to be a space scientist someday. Well, I wanted to be an astronaut, which we all thought was exactly the same thing as a space scientist. It's not quite, but close enough.
Rocket scientist. Yeah, we're called rocket scientists.
And of course, by the time I got to high school, I kind of gave up on that as a dream that could never come true. And I went to college and I studied physics, and then I decided to kind of go into geophysics. And then when I went to graduate school at Penn State, by some wild coincidence, one of the other grad students was a Caltech grad who had worked at JPL for a couple of years before getting his PhD, and we got to be friends. And he said, "Oh, the Viking mission is going to Mars next summer, and I know a couple of scientists there that are looking for summer interns. You ought to apply." And I thought, I could apply to that. I could actually go and actually work on something in space. So I applied, and I got selected, and I went to JPL for the summer, and then I went back to Penn State at the end of the summer, and again, one of those wild coincidences, my graduate advisor got a job at a university back in California and invited me to come back with him. And I went to JPL and I said, "Can I work here part-time while I'm working on my PhD?" And they said, "Sure." And I grabbed onto JPL, and I never let go. This is the only job I've ever had in my life, other than working in the tire shop during the summertime. So that's my gravity assist. It's like, I've always wanted to work in space. I sort of lost the faith for a while and wandered in the wilderness, but by luck and being at the right place at the right time, here I am today.
Yeah, sometimes it takes several gravity assists to get
Yeah,
us
that's
in the
right.
right direction. Yeah, indeed. Well, it's really been a delight, Bruce. I thank you so much for coming on and telling us all about InSight.
Well, I don't like talking about anything more than InSight except maybe my kids. So this has been fun.
Thank you. Well, until next time, this is Jim Green, and this has been your Gravity Assist.